Hello, welcome back to MEC 416/816 Engineering Acoustics. In this video, we're going to go through what is known as the acoustic intensity. So the instantaneous acoustic intensity, or big I of T, of a sound wave is the rate per unit area at which work is done by one element of a fluid on an adjacent fluid element. So these elements, as we divide them up, are pushing against each other, causing them to expand and contract, and therefore are doing work on each other. It is defined as big I, which is now a vector of time, is equal to the pressure times the fluid particle velocity u. It has units of watts per meter squared. So then the intensity, in fact, let's add a little I here to represent that this is the instantaneous intensity. So the intensity I is then going to be the temporal average of that instantaneous intensity. So we can write that big I is equal to the temporal average of big I sub I, which is a function of time, again with respect to some period, that then is equal to the temporal average P times U vector, again with respect to time, some period t, is then equal to 1 over big T times the integral from 0 to t p u dt, and that is our acoustic intensity. And so for a wave consisting of a single frequency, t is the period. If the wave does not consist of a single frequency, then you need to make a decision on what you're going to use for that period. And generally, you might consider finding if the frequencies are commensurate, then you could find a common period. If not, you might just want to choose the period of the lowest component. Or alternatively, you could do some kind of decomposition and break it up into components where you have a single, where each component has a single frequency, and then you could find the acoustic intensity of each of those and then add those up together in some way. Okay, so for a plane harmonic wave traveling in the plus or minus x direction, we can write that P is equal to plus or minus rho times C times U. And note that, let's just write that note, that U is not a vector here because we're only considering one-dimensional propagation. Because we're dealing with plane waves. So then we can compute our acoustic intensity I as being I equal to plus or minus the amplitude of that pressure wave, and we're going to use a big P here. In fact, let's use a script P. So that's the amplitude of the wave divided by 2 rho 0 C, and that's the amplitude squared, which can be written as the acoustic, I'm sorry, this should actually be not the amplitude, it should be the total pressure. So we can write that then as P, the acoustic pressure plus the atmospheric pressure, P0, divided by 2 rho 0 C, and there should be a plus or minus in front here as well. And that is our acoustic intensity. And this is only true for plane harmonic waves, and it's going to then be approximately true for diverging waves at great distances. So if you're not dealing with if you're using a real source, then at far away from that source, this will be approximately true, and it's only true for exactly plane waves. Okay, in the next video, we're going to go through the decibel scale. Thank you.